Hi, everybody. Thank you for coming to the Weekend AIP seminar today. So today I'm very happy to have a speaker, Antonin Schrab. So Antonin is currently a PhD student on the Foundational Artificial Intelligence CDT at University College London, supervised by Benjamin Gurch at the UCL Center for Artificial Intelligence and Arthur Gretton at the Gatsby Computational Neuroscience Unit. Today, he will talk about Mmd Aggregated Two-Sample Test, KST Aggregated Goodness of Fit Test. So, okay, so please, Anthony, please start.
Hi, well, thanks for a great introduction and for inviting me. So yeah, I'm Antonin, and today I'll present my work on Mmd Aggregated Two-Sample Test. And if we have time, I'll also discuss the KST Aggregated Goodness of Fit Test. So as I said previously, if you have any questions, feel free to interrupt me. So just as an overview of the talk, so I'll start with our aggregated MMD test, presenting the two-sample setting, introducing the MMD test, the aggregated test, and running through experiments. And then I'll do the same for the KST aggregated goodness of fit test if we have time. So let's first start with the MMD aggregated two-sample test. So this is a paper done in collaboration with Gilmour Kim from Yonsei University, Mélisande Albert and Béatrice Laurent from Université de Toulouse, and Benjamin Gurch and Arthur Gretton, my two supervisors at UCL. So two-sample problem. So what is the two-sample problem that we'll be dealing with? So we're given independent samples. So a two-sample problem, we're given independent samples, samples x1 up to xm drawn from some density p in RD, and some sample y1 up to yn drawn from another density q in RD as well. And we ask the question, can we decide whether or not p is equal or different than q? So we have two samples and we want to know if they come from the same distribution or not. So we'll be working in a non-asymptotic regime. This means that we won't be assuming that our test statistic behaves as an asymptotic distribution. And we'll be working with balanced sample sizes. This just means that there exists some constant such that n is smaller than this constant times m. So in practice, this just means that we cannot consider a case where we fix one sample size and let the other sample size go to infinity. And as convention, whenever I write t, it can be any constant, not necessarily the same as the previous t. And so we can frame this two-sample problem as a statistical hypothesis testing problem, where we test the null hypothesis H0 of P equal Q against the alternative hypothesis of P different than Q. And if we have a hypothesis test delta, that's a function that takes as input all the two samples, and it will return 1 if we reject the test and return 0 if we fail to reject the test. So what is a good test? So by design, the probability of a type 1 error is going to be controlled by alpha. And the type 1 error is the probability under the null hypothesis. That's when xm and yn are both drawn from density p. It's the probability that this test rejects the null hypothesis, so that it makes a mistake. And just by design, this probability is going to be controlled by alpha. And then the aim is to beta control the probability of type 2 error. And the type 2 error is under the alternative when p is different than q, our test fails to reject the hypothesis, so it outputs 0. So the aim is to bound this probability. And the intuition we have is that if P and Q are really close to each other, in the sense that the L2 norm of P minus Q is small, then it's going to be really hard to distinguish between P and Q. So we might not be able to beta control this probability. And so we arrive at uniform separation rate, where we can ask some question. We say, what is the smallest value of the L2 norm of P minus Q, which always ensures that this equation star holds for any P and Q, such that the difference P minus Q lies in some class of function, which we'll specify later. And so we can rephrase this as what is the smallest value delta, such that we have our test is able to beta control this probability of type 2 error against all the hypotheses satisfying the two conditions that P minus Q belongs to that class of functions, and that we have the L2 norm of P minus Q is greater than delta. So this is equivalent to what was written before, and we write it this way so that we can define the uniform separation rate in mathematical terms, where we have an infimum over delta. This is what is the smallest value delta. Then we have a supremum where we consider all the alternatives P and Q, such that P minus Q is in P, and L2 norm of P minus Q is greater than delta. And then this part in blue is simply saying we beta control the probability of type 2 error. So this is the definition of uniform separation rate. And the rates we'll consider, at least in our work, are of the form some constant times m plus n to some negative power. So this is really a rate. And this is intuitive because as the sample size grows, this rate should go to 0, in the sense that the more samples we have, then the more we'll be able to detect small differences between P and Q. And if we have infinite samples, then we're able to detect any difference between P and Q, or at least speaking loosely. And so this means that the uniform separation rate should go to 0 as the sample size grows to infinity. And then we can ask what is the best uniform separation rate the test of level alpha can hope to achieve. And so this is called the minimax rate, and it's simply taking the infimum over all the uniform separation rates, where the infimum is taken over all possible tests of level alpha. And we denote this by rho with an underscore. Yeah. And then the aim, and the reason I've written hope to achieve is because, like, we don't know if the infimum is actually achieved, if there's a test that matches this rate, this minimax rate. And so the aim for this work is to construct a good test, in the sense that it is optimal in the minimax sense. This means it's going to achieve this minimax rate, or at least up to some log or log term. And we want our test to be adaptive, in the sense that it does not depend on any unknown parameters of this class of functions C, which I haven't yet specified. So we're asking what class of function should we use for C. And so C is, as a reminder, is we assume that the difference between P and Q lies in C, but we don't have assumptions on regularity on P and on Q, but only on the difference P minus Q. And so as a class of functions, we'll use the class of smooth functions called Servo Levels. So these are functions that lie in L1 and L2. So they're integrable and square integrable. And we have this, this integral over the term here, and we want this to be bounded. And so we have some radius R, and we want that integral to be bounded by this radius. We have a smoothness parameter where in the integral there's an L2 norm of psi raised to some power 2s, where s is a smoothness parameter. I'll explain why we call it the smoothness parameter later. And the dimension, and here we have this Fourier transform term. So this is an integral in the Fourier domain, and we want this to be bounded. And it is well known that the minimax rate over Servo Levels is n plus n to the power minus 2s divided by 4s plus d. So everywhere I write n plus n, and often this will be only n or something, but because we assume balanced sample size, can always replace n with m or with n plus n essentially. And so the aim is to construct an adaptive test in the sense that it is a test that does not depend on S and does not depend on R, the unknown parameters of the Servo Level. And so just as an illustration, here I'm plotting some functions that lie in the Servo Level. These are perturbed uniform densities. So the x-axis is just x, and the y-axis is our density. So this is with one perturbation, and those functions have been shown to belong to the Servo Level. And we can see that as we increase the smoothness parameter, essentially the curve becomes more smooth. So for very small s, we have kind of large perturbations, but for large s, then we have very, very small perturbations. And this is the same case here with 3 perturbations and with 4. And by perturbation, I mean that it goes one up and one down. So these are some functions that belong to the Servo Level. So we've now introduced the 2-sample problem, and we're now going to introduce the Mmd test, and we'll then introduce our aggregated test. And we're going to consider uniform separation rate of these tests. So first, so the Mmd is a kernel-based discrepancy. So we need to talk kernel. Kernel can see it as a positive definite function from Rd cross Rd, and it's a real valued function. And then we work with a reproducing kernel Hilbert space, RKHS. This is an inner product space of real valued functions, satisfying the reproducing property, those two properties. If you're not familiar with RKHS, you can just think of it as a space of smooth functions. We'll be working with a translation invariant kernel of this form, where it is essentially a product of kernels in each dimension. And it's translation invariant because here we have the xi minus yi. And this is for some functions k1 to kd, which lie in L1 and L2, and we scale them so that they integrate to 1. We scale them so that they integrate to 1 just for our theoretical result. In practice, this does not really matter. And the bandwidth, then once we have this kernel, we can consider some bandwidth. This is a vector with d components, all positive. And then the function defined as k lambda, where we scale the x minus y by xi minus yi by lambda I. and this is also a kernel. And here we've added a term, a multiplicative term on the outside so that we still integrate to 1. But as I said before, this term can be removed in practice. So this is for the kernel. So now we have a kernel with some bandwidth, and in this work, we'll be interested in how to choose this bandwidth and what are the impacts of choosing the bandwidth. So 2 common examples that lie within this definition of kernels are the Gaussian kernel, where we simply define the Ki to be 1 over square root of 5, it's just normalizing constant times exponential of minus u squared. And if we do this, we get the Gaussian kernel, where here we can see that this is an L2 norm, especially if all the lambda i's are the same, then the lambda comes out of a sum, and this is exactly an L2 norm squared of x minus y. And so if we have a very small bandwidth, so here I'm plotting only the exponential function here with the yi is equal to 0 and the x is the x-axis. So if we have a really small bandwidth, this is essentially going to go almost to a delta function as lambda goes to 0. And as we get a larger bandwidth, then we just have our Gaussian with a larger standard deviation. And similarly, for the Laplace kernel, this is defined for some Ki equal 1/2 of exponential of minus absolute value of u. So basically, we've dropped the square in here. And now we can recover a term that looks like an L1 norm, especially if all the bandwidths are equal, then we take it out, and this is exactly the L1 norm of x minus y. And again, like a small bandwidth looks like this, and as we increase the bandwidth, it increases the bandwidth. So it's wider and wider. So now we're going to build some 2-sample tests based on the maximum mean discrepancy. And so what is the maximum mean discrepancy? It's defined, the Mmd is defined for some P and Q, the density, as the supremum over all the functions f in the RKHS, such that the RKHS norm is bounded. So this means it's smooth functions. And then the supremum is over the difference in mean, where we have the mean of f of x with respect to p and the mean of f of y with respect to q. So as an illustration, if we have some samples where p is different than q, and we compute this witness function f, so it can be shown that the witness function f is going to be a sum of kernels centered at all our points, essentially. So here we can see that's the kernel in here. And because we have many points, the kernel gets bigger. And so if we have a bandwidth that's too small, like in this case, we really have a lot of wiggles here. But this is the case where P is different than Q. So what we really want is that the witness function on the blue point is quite high, and the witness function on the red point is quite low, so that the difference in mean will be quite large. So this still works for bandwidth too small. And so if we consider well-calibrated bandwidth, that's the witness function we would get. And if the bandwidth is too large, then essentially this is not going to work well, because even though P is different than Q, this is going to give us a small MMD. And for the case P equal Q, if the bandwidth is too small, then again, we just get some bumps over every point. And essentially, even though P is equal to Q, here the mean of the blue ones will be quite high and the means of the red ones will be quite low. So the MMD will be quite large. So this would be wrong in the sense that we would get a large MMD even though P equals Q, and this is due to the fact that we chose a bandwidth which is too small. For a well-calibrated bandwidth, we would get a function like this, and because we're restricted to some smooth functions, this function is not allowed to jump up and down to be very wiggly. And if the bandwidth is too large in this case, we'll almost get something flat. And so this was just for some samples, but of course this also applies to the case of density. So this is for the Gaussian and the Laplace density, and we plot the witness function. All right. And so one property that we assume on our kernel is that the kernel is characteristic. So this is a bit technical. If you're interested, you can read the reference of Fikumi Duenao, but essentially all you need to know is that the Gaussian and the Laplace kernels are characteristic. And so what does it mean to be characteristic? Well, it's a property that ensures that the MMD is going to be 0 if and only if P equals Q. So this is something we need in order to construct a test based on the MMD. So I hope I've illustrated that the choice of bandwidth is important, but we can summarize it like this. If we have some small sample size, then an MMD test is only going to be able to detect some global differences. So for small sample size, if we have a bandwidth that's too small, then we'll wrongly detect artificial local differences under the null hypothesis. This means that even though even though P is equal to Q, if we really look on a really small scale, then we're going to be able to find some difference, but this difference is going to be artificial, so it's not something we want. And for this case, if we have a large bandwidth, then that would be well suited to detect the difference, which are global between P and Q. And if we have some large sample size and the local differences are also detectable, in this case, it'll be the opposite. And a small bandwidth is going to be well suited to detect those local differences between P and Q, while a large bandwidth will fail to detect those differences. So essentially, the intuition is that the bandwidth should decrease with the sample size as the sample size increases. I hope that's clear. So yeah, as I hope I've convinced you, the choice of kernel bandwidth is crucial for test power for an MMD test. And some common methods to choose the bandwidth that are used in practice, or to either use some heuristics like the median heuristic, or we can use some standard deviation. And this is defined as the median between the L2 norm of the differences of the points in the pooled sample that we consider all the samples both from P and from Q. And we just set the bandwidth to that value. And this is just a heuristic, and it has no power guarantees. And this was first proposed by Gretton and Al in the paper where they introduced the MMD test to sample test. And another approach is to use data splitting, where we split the data in two parts. On the first part, we select some bandwidth that maximizes proxy for asymptotic power. And on the second part, we perform the MMD test with a selected bandwidth. And so this has asymptotic power guarantees, but however, when the sample size is low, it often results in low power. And just the fact that we run the test on less data is going to result in a loss of power. So this was first proposed by Gretton and Al for the linear time MMD estimator. And this was then extended to a case of a quadratic time estimator by Liu and Al. And in our paper, we propose a new method which aggregates multiple tests with different bandwidths. And so this method avoids to use arbitrary heuristic or to use data splitting, and we'll have non-asymptotic power guarantees that we prove, and those are in terms of non-asymptotic uniform separation rate and minimax rate. All right, so now let me introduce the two-sample Mmd test for fixed bandwidth. So the maximum mean discrepancy can be shown to be equal to this term, where we have some expectation of a kernel over X minus some expectation of a kernel over P minus some expectation of a kernel over P n over Q times 2 plus some expectation of a kernel over Q. And so the quadratic time estimator can be obtained by just replacing those expectations with some averages. So then we need to construct a quantile. So to do this, we need to simulate the null hypothesis. And we can do this by repeating B times the following process. We generate some permutation sigma. We permute the elements of the pooled sample, so of xm union yn. Essentially, we just shuffle them and we split them in two groups. We obtain our xm sigma and yn sigma. Those are our permuted samples. And then we compute the MMD with a permuted sample. So the intuition here is that under the null hypothesis, P is equal to Q. So the samples, so all these points are drawn from P equal Q. So all these points also drawn from P equal Q. So that's how we can simulate the null hypothesis. And then we simply define our quantile to be the B plus 1 times 1 minus alpha's largest value of the B permuted test statistic. These are these guys that we would obtain for some sigma 1 all the way to sigma B, plus the original test statistic. This is this guy over here. And the reason we also include the original test statistic, this is so that we can obtain a non-asymptotic level of our test using an argument based on Romano and Wolf result. And so when we finally able to define what a single test is, so we have some well-calibrated non-asymptotic level, as I've said, and the test is defined as rejecting the null hypothesis if our MMD estimate is greater than the quantile we've estimated. And so this was using permutation. Now we can also simulate the null hypothesis using a wild bootstrap in the case where M is equal to Q. So now we consider a different quadratic time estimator. It's quite similar, but it misses some terms where it misses the term xi, yi, essentially, because here the sum is over I different than j. And so the wild bootstrap works by, we generate some random active random variables. These are just variables that take the value -1 or 1 with equal probability. And instead of having the normal MMD estimator, we multiply by those random variables. And in our paper, we show that this is actually equivalent to using some permutation. And yeah, so if you're interested, you can have a look at it. And so then we just define the quantile in a similar manner as before, and the single test as well. And we also show for both tests that they have non-asymptotic level alpha. And so now we have some theoretical results about uniform separation rate of this single test. So I'll just recall the minimax rate over Servo Levels is this m plus n to the power minus 2s divided by 4s plus d. And now if we fix our bandwidth, as I mentioned before, the bandwidth should depend on the sample size. So if we fix our bandwidth to be this this quantity, which depends on s, then we can show that we obtain exactly the minimax rate. This means that the uniform separation rate of this test with this chosen bandwidth lambda star is upper bounded by some constant times the minimax rate. But so this looks like this test is optimal, which is great, but it is not adaptive over Servo Levels because this choice of bandwidth depends on this unknown parameter s of the Servo Levels, and this means we cannot implement it in practice. So what we're going to do is aggregate several bandwidths so that we're able to obtain a good rate, but without setting our bandwidth with respect using the unknown parameter, essentially. So now we're going to do this for the Mmd Aggregated Test. So let me introduce it. As a reminder, we've just said the single test is defined as rejecting the null hypothesis if Mmd is greater than the quantile. And this is for fixed bandwidth. And then we define our aggregated test as, so this is for a collection of bandwidth lambda, a finite collection. Actually, this holds for a countable collection, but in practice, it needs to be finite if we want to implement it. And this rejects the null hypothesis if the Mmd is greater than the quantile for some lambda. So, and this is important here, the quantile, like it's a different quantile for each lambda. And of course, if we do this, we would get some wrong level. So how do we ensure we get the correct non-asymptotic level for our test? Well, we change the level here and we introduce some positive weights, W lambda. Those are some weights which sum to 1 or sum to some value smaller than 1. And those weights can be chosen by the user. And we also introduce some correction, which is defined exactly so that our level has our test, has level alpha. So this U alpha is going to be some supremum over U, such that essentially the probability of doing a type 1 error is smaller than alpha. So why is this the probability of doing a type 1 error? So first of all, it's the probability under P times P, that's under the null hypothesis. And then here, if we go back to our aggregated test, saying that the Mmd is greater than the quantile, the same as saying that the Mmd minus the quantile is greater than 0, and saying that this happens for some lambda, the same as saying that this happens for the maximum value. If the maximum value is greater than 0, then it means that this happens for some lambda. All right, so if we define U alpha like this, we get a test, an aggregated test with non-asymptotic level alpha as desired. In practice, we need to estimate the supremum. We do this using a bisection method. So because this is really finding some root of this guy is a function of U, and then we want that function of U minus alpha, and we want to find its root because this is an increasing function of U. And there's also this probability here that we need to estimate. So we do this with a Monte Carlo approximation in a similar manner than with have introduced before, using either some permutations or some wild bootstrap. And essentially, we replace this value with a new wild bootstrap or permutation test statistic. And then this is just an average. And in our paper, we actually show that the test with those two approximation steps is still of non-asymptotic level alpha. So this is for MMDAG, our aggregated test, Mmd test. And we provide some theoretical results as well. So now for a specific collection of bandwidth, lambda star of the form here 1D is just a d-dimensional vector consisting of 1. And then we multiply this by some power of 2, where negative power of 2, where the L is between 1 and this number that depends on M, on N, the sample sizes, and on the dimension D, but that crucially, this number does not depend on S. So this is computable. And then we have some weights. Here the weights are of the form 1 over L squared times some constant. And they are of this form so that even if L goes to infinity, this will still sum up to 1 or smaller than 1 for finite L. And so this test with this design collection of bandwidth, we show that it's almost optimal in the sense that it reaches the minimax rate up to some log-log term, and it is adaptive in the sense that it does not depend on the smoothness parameters S and R of the Servo Levels. So here we can see that the price to pay for adaptivity over the Servo Levels is just this iterated logarithmic term in the minimax rate. So just as a quick summary, so for the single test, this is for a fixed bandwidth. We can show that for some specific choice of bandwidth, it's optimal. However, the specific choice of bandwidth depends on S, so it's not adaptive. And for MMDAG, this is for a collection of bandwidth, capital lambda, and for a specific choice of collection of bandwidth, which does not depend on S, we obtain the minimax rate up to some iterated logarithmic term, and our test is adaptive over S and R. So this is it for the theoretical results. Now we can move on to the experiment.
Sorry, can I ask you a question?
Yeah.
So you said a single test depends on the S parameter, right? But so MMD aggregated test also seems like the S is there.
I didn't understand your question, sorry.
Single test is
so here
on the this like a red S, right?
Yeah.
And so the conclusion for the first one is like it doesn't depend on the S, or still it depends on S. So this
so essentially I'm saying if someone gives us the smoothness parameter S, we would be able to set our bandwidth like this, and then we would get an optimal, we would attain the minimax rate. However, we do not have access to this S. So in practice, we cannot, so we know that there exists some bandwidth such that the test can be optimal, but we do not have access to its S parameters, so we're not able to set the bandwidth like this.
Right. So then how about the MMD aggregated one? Still it does depends on the S or not?
No, so here nothing, this doesn't depend on S, yeah. So that's the whole point. And essentially the intuition is that we show that this collection of bandwidth is gonna incorporate the one not incorporate the previous one, but it's going to be enough to be close to the previous lambda star that depended on S, but this does not depend on S.
Okay. Oh, very nice. Thanks.
Yeah, you're welcome. Are there any other questions? All right, there's no more questions. I'll continue. Oh yes, so this depends on S. This is just the minimax rate. That's not how we set our pen. Maybe that was the confusion. So we can move on to the experiment. So as I said, we had some weights, and the weights could be chosen by the user. So I'll now discuss how one can choose the weights. We propose 4 strategies. So first, we consider the median bandwidth. So that's defined in a slightly different way as I defined it before. And here it's essentially, we take the median in each component. So this is some Zi, Z prime I. So it's the median distance in each component for all the points in the full sample. And we consider in our experiment some finite collection lambda of bandwidth. And those going to be just some bandwidth that are the median bandwidth scaled by some powers of 2, where L minus is smaller than L plus, and those can be either negative or positive or 0. And so here we just use this notation lambda subscript J to denote the ordered bandwidth. And then we propose 4 different weighting strategies: some uniform weight, increasing weight, decreasing weight, and centered weight. Here the constants are just here so that the weights sum up to 1. So this is how they're defined mathematically, but I guess it's easier to understand with a plot. So here we plot those weights for 5 bandwidth and for 6 bandwidth, where on the x-axis is our bandwidth sorted in increasing order, and the y-axis are our weight values. So the uniform weights are just the same for all the bandwidth. The increasing weight increases, the decreasing weight decreases, and the centered weight put the highest weight at the center of a bandwidth. This is for some odd number of bandwidth, and this is for some even number of bandwidth. So in our theoretical results, as a reminder, the weights were of the form 1 over L squared. So here it's with some J, but essentially like an equivalent way would be J squared, but we decided to define them just 1 over J. And the reason for, instead of J squared, the reason for that is because if we use J squared, then our weights will actually get really small really quickly. So here we're already at 0.1 for using only 5 bandwidth. So if we square this, we'll be very close to 0. And the intuition we have is there's no point giving some, in practice, giving some bandwidth, some weight extremely close to 0, because that would mean we're not really interested in having this bandwidth. And if we're not interested, then we might as well not include it in our collection of bandwidth. So that was the intuition. All right, so for the experiments, we have this Mmd experiment where we consider some per tube uniform densities. So those, as I shown before, those belong to the Servo Levels. So here the blue one is just one perturbation. The red one would be 2 perturbation, and so on. On the left, it's in dimension 1. And on the right, it's 1 perturbation in dimension 2. This is 2 perturbations in dimension 2. This is 3 perturbations in dimension 2. And as I mentioned before, those functions, I think, were first introduced by Bootstrap in AL, and they are used in the proof of the Servo Levels minimax rate. So what we're going to do is we're going to test the uniform density. Uniform density against this perturbed uniform density. So first we do this in one dimension with sample size 500. So we consider both the Gaussian kernel and the Laplace kernel, and we vary the collection of bandwidth. The collection of bandwidth increases from left to right. The values of a bandwidth increases. The tests we consider are our Mmd Ag test with uniform centered increasing and decreasing weight. We consider the median test. This is just, we use the MMD where we set the bandwidth to be the median heuristic. We consider the split test where we split the data in half, and we use the first half to select the bandwidth that maximizes a proxy for asymptotic power, and we use the second half to run the test. And the oracle here is just the same as the split test, but on twice the sample size. So here, all our tests have access only to 500 data points. So the split will use 250 to select the bandwidth and 250 to run the test, while the oracle will have access to 500 more samples, and it would choose an optimal bandwidth on this, on those 500 more samples, and will then run the test with that optimal bandwidth on the original 500 samples. And the OST test, the one-sided test, this is a test that uses post-selection inference. It was introduced by Kugler and al., the learning kernel test without data splitting paper. But this test, like all the other tests, use some quadratic time estimator, while this test OST uses some linear time estimator, MMD estimate. So it's normal to see that it does not perform as well, but we included it nonetheless because this is the only MMD adaptive test out there. And the reason they use a linear time statistic is because they work in the post-selection inference setting. And so in order to use the polyhedral lemma, they need some asymptotic normality, and this holds for the linear time MMD estimate, but not for quadratic time MMD estimate. All right, now we can dig into the results. So on the x-axis, we've got the number of permutations that increase from 1 to 4. And on the y-axis, we have the power. So we see that as the number of permutations increase, like the power decreases as the problem becomes harder. And so we observe that the oracle test performs the best. And then our 4 different Mmd Ag tests outperform the 3 other tests in almost all the settings. Maybe here it just matches, but the 4 Mmd Ag tests outperforms the others. And so it's great to see for us. And we can see that in some cases, it is even quite close to the oracle test, even though as for perturbation, for 3 and 4 perturbations, it's still higher. And essentially, where we don't observe that much difference between the Laplace and the Gaussian kernel, the Gaussian performs better, slightly better, but as we'll see in other experiments, then the Laplace sometimes performs better. So the intuition between the 3 different columns is the first column, we have some collection of bandwidth. And if we just look at our 4 Mmd Ag tests, we observe that the one with increasing weights performs the best. So this means that putting the most weight, the highest weight on the biggest bandwidth gives us the best result. So this is kind of saying the best bandwidth in your collection is the biggest one. So maybe you should consider some bigger bandwidth. So that's what we do in the middle column. So in here, we have considered like larger bandwidths. So as a reminder, this means that this is the lambda, this is the median bandwidth. scale by 2 to the minus 4 to 2 to the 0. And then we observe that the centered and the centered test performs the best. So this really means that the bandwidth in the middle of our collection performs the best. So if we keep increasing our collection of bandwidth, increasing the bandwidth in our collection, then we observe that the decreasing weight Mmd performs the best. So this would tell us that actually the best bandwidth is the smallest one, so we should consider a smaller collection of bandwidth. So I think this intuition is quite interesting, but however, in practice, like we cannot just run our test with some collection of bandwidth, compare the results, then change the collection of bandwidth and run it again. But however, I think this is quite interesting. So for the perturb uniform in 2 dimensions, this is, we observe similar results essentially. So we now use sample size 2000. And again, our 4 tests outperform the 3 other tests. The oracle works quite better than our test here. And we observe the same trend of the increasing centered and decreasing bandwidth performing the best. And here it looks like the Gaussian kernel performs better. But this is quite similar to a previous experiment. And then we consider another experiment with some MNIST digits where we will test, so P is just any digit, and we test this against the odd digit, only the odd digit, the odd digits with 0, the odd digits with 0 and 2, with 0, 2 and 4, and with 0, 2, 4, and 6. So comparing P to Q1 should be relatively easy, while comparing P to Q5 should be relatively hard because the only difference is that we miss an 8 essentially. And so those are MNIST digits that we actually consider downsampled images to 7x7 resolution. And this was in order to match the experiment that was proposed by Kugler and al. So that's why we've done this. For our KS-DAG experiment, we actually run some experiments on MNIST in 28x28 resolution. So this was not done for some computational reasons. It was just too much to experiment. And those images are in dimension 49. However, the problem of distinguishing digits is inherently lower dimensional. And so when we run our experiment, what do we observe? So this is the MNIST experiment. We use 500 sample sizes. And now our MMDAG test really outperformed the 3 others, but also matches the power of the oracle test in almost all of the experiments. So this is really interesting. So at first it might look like a bit weird since it's oracle, it's supposed to have access to the best bandwidth, but as a reminder, the way it chooses the bandwidth is it chooses it by maximizing a proxy for asymptotic power. And here we're in dimension 49, we use only 500 samples. So essentially, I think we haven't reached the asymptotic regime at all. And so this proxy for asymptotic power is not that good of a proxy. So that's why we're able to beat that oracle test in some settings. And yeah, as I said before, here we now observe that Laplace kernel works better than Gaussian, while before was the opposite. So there's not one kernel that always works the best. And one last experiment for MMDAG. So this is just an experiment where it's essentially each column represents the 3 experiments that I talked before. So this is the uniform perturb density with 3 perturbations in dimension 1. This is in dimension 2 with 2 perturbations, and this is the MNIST case with Q3. And here what we're doing is we are considering a wider and wider collection of bandwidth so that we have more and more bandwidth in the collection. And we do this for the uniform and centered weights. And what we observe is that our power doesn't decrease that much as we increase the number of bandwidths in our collection. So this is quite interesting, and especially that in practice, we don't have really prior knowledge about where the bandwidth is. We might not have prior knowledge about where the best bandwidth is located. So it's really interesting to see that if we just think, oh, it's going to be between 2 to the minus 10 and 2 to the 10 times the median bandwidth, then we don't lose that much by just considering more bandwidth. So that's really important to use our test in practice. And by the way, the different weighting strategies, they can be seen as incorporating some prior knowledge into our test. We have a collection of bandwidth. If we have some prior knowledge where the best bandwidth might be, well, we can put the most weight on there. So as a conclusion for Mmd, so we have we propose an aggregated Mmd test with different kernel bandwidths. So right now I've talked only about different kernel bandwidths, but actually the whole procedure just works for different kernels. They don't need to be a fixed kernel where we vary only the bandwidth. However, the theoretical results are really for bandwidth selection. This test does not use data splitting. And then we have the Mmd theoretical results. We prove that our test is optimal in the minimax sense of a Sobolev-Bol up to some iterated logarithmic term. It is adaptive over those Sobolev-Bols in the sense that it does not depend on S, it does not depend on R. Our theoretical results hold for both the wild bootstrap estimation of a quantile and also the permutation-based estimation of a quantile. And it holds for a wide range of kernels, which is quite important because previous work only focused on the Gaussian kernel, while now essentially it holds for any product of the kernels that lie in L1 and L2. And in our experiments, we observe that our Mmd test outperforms state-of-the-art Mmd adaptive test. So I think it's already 10 in the UK, so 7 in Japan. Do you think I should continue and try to go quickly through this, or should we stop here?
Yeah, you can continue.
All right, should I aim to go quickly, like 10, 15 minutes? Or?
Sure.
Yeah, okay. So now we're done with Mmd. So we'll talk about KSDAG, which is a KSD aggregated goodness of fit test. And this is a written paper that I've done with my 2 supervisors, Benjamin and Arthur. So we'll introduce the goodness of fit problem and the KSD test. We'll look about uniform separation rates and have more experiments. So what is the goodness of fit problem? You're probably familiar with it. Right. We're giving a model, so that is a probability density P, and this is on RD, or actually it's enough if we're just given the score function. So the score function is the gradient of the log density. So we're given some model P, and we're given some samples, Zn, which are IID drawn from some density Q. And as before, we ask the question, is P equal to Q or is P different than Q? So we're given some samples, we're given a model, we want to know if the samples come from this model. And to do this, we can use a Stein kernel. And so this K lambda is just the kernel that we used for the Mmd case. And then we define a Stein kernel HP of lambda, which depends on P and depends on lambda. It's essentially this kernel. And here, as you see, only the score function appears. We never need only P. So as long as we have the score function, we can compute this Stein kernel. However, this Stein kernel is not translation invariant, while our K was translation invariant. And so this is gonna make the thing quite more difficult to work with, as I'll mention later. The Stein kernel satisfies the Stein identity. This is just the expectation of a Stein kernel with respect to P is equal to 0. And the kernel Stein discrepancy is simply the Mmd with the Stein kernel. So we just substitute the Mmd, so the three terms, the expectations, and because of the Stein identity, those two terms with expectations with respect to P will just be 0. So they disappear. So we just have that the KSD is the expectation with respect to Q of the Stein kernel. And of course, we don't have access to Q. So we use a quadratic time estimator where we just put an average instead with our sample. So this is a U statistic, not an average, sorry. It was the same before. And those tests were first introduced in these two papers that were in ICML 2016. So we can use a wild bootstrap exactly as before, but now with a Stein kernel. So we sampled some epsilon I from uniform Rademacher variables. So that's just, they take values -1 or 1 with equal probability. And we can also do a parametric bootstrap. So the parametric bootstrap, it assumes that we're able to sample from our model P, which might not always be the case, because to run the KSD test, we only need access to the score function. So we might know P only up to normalizing factor, or even we might not be able to sample from P even if we have P. So the parametric bootstrap, yeah, is just computed as we sample some new points from P, so from the model, and we compute the KSD estimate. And the quantile is, as before, just defined as the B1 minus alpha largest value of a B bootstrap test statistic, either with wild bootstrap or with parametric bootstrap. So for the wild bootstrap, we actually obtain only asymptotic level alpha. The argument that we used before were based on the Romano and Wolf result to obtain non-asymptotic level does not work in this case. So that's why we don't include the original statistic in here as well. And however, for parametric bootstrap, we're able to get non-asymptotic level, but this comes at the cost of assuming we can sample from P. So as before, the single test is just defined as rejecting the null hypothesis if the KSD is larger than the quantile, and the aggregated test is defined as rejecting if the KSD is greater than the quantile for some lambda. And this is given some weight that the user chooses, and for the level correction defined as before. So in terms of uniform separation rate, so if we let the diamond operation be the integral transform, that is, we're giving a kernel kappa, that's the integral of kappa xy fx dx. And here, if kappa is translation invariant, this is a convolution. And we assume that the kernel, the expectation of our Stein kernel under Q, of our Stein kernel squared, is finite. So what can we say in terms of uniform separation rate? As a reminder, what is the uniform separation rate? So uniform separation rate is a condition such that if the L2 distance between P minus Q is greater than some delta, then we guarantee that we have beta control over the probability of type 2 error. So this really means that this guy here is a uniform separation rate. So let's look at this guy. What do we have? First, we have a minimum over our collection of bandwidth. So actually, this is the result for the KS-DAG. But if we just look at the result for the KSD single test, then we will just have those two terms without this minimum and without the weight in here. So we have those two terms. If this kernel was not the Stein kernel, but was the K, like we had for the Mmd K, then this would be some bias term here, this L2 norm, and this diamond operation would be some convolution because our kernel was translation invariant. The whole problem comes from the fact that H is no longer translation invariant. So this means that because the way the proof was we did the proof in MMDAG was here we have, as I said, K, and this is the convolution. Then we use Plancherel's theorem to say that this L2 norm is the same as the L2 norm in the Fourier domain. Then we have a very nice property that the Fourier transform of a convolution is the product of a Fourier transform. And this reasoning does not hold anymore with this more general diamond operation that when we don't have translation invariant. So because we're not able to transfer to the Fourier domain using this argument, essentially we're not able to obtain rates over Sobolev anymore. And this other term here, this comes from a variance term actually. And yeah, here we have the A lambda that is defined here. It's our assumption that it's finite, but crucially, this value depends on lambda. So that's our theoretical result for a uniform separation rate. And we'll do the experiment and we can wrap up. So I've got two experiments. The first one is some Gaussian Bernoulli restricted Boltzmann machine. So this is just a graphical model with a binary hidden variable H that is just binary, so either -1 or 1, and this is in dimension 40. And we have a continuous observable variable Z in dimension 50. And they are defined to have joint probability density PZH as follows, where we have some constant term, that normalizing term, and then an expectation with those guys, where we have some parameters, some capital B, some lowercase b, and some the lowercase b and the lowercase c. We initialize them as we just draw them from some like standard Gaussian distribution, and the b, they're just random variables, so either 1 or -1 in dimension 50 times 40. And the probability density P is intractable. So like, and the reason it's intractable, so we can obtain it just by modularizing over H, but this is in dimension 40. So for that reason, it's intractable. So we don't have access to P. However, we do have access to a score function. So we don't need to know this normalizing term. There's a closed form for the score function. And in our experiment, so the model we consider is this P, so defined like this, where we have access to a score function with those initialization, and the samples we consider are going to be obtained from also a Gaussian Bernoulli restricted Boltzmann machine. And we sampled from it using a Gibbs sampler, but now we're going to inject some noise in the entries of the beat of this beat. So this B is a matrix of -1, 1. And we essentially just inject some noise with standard deviation sigma and into those entries. So P is going to be different than Q and more different as sigma increases. So our result here, we use a collection of bandwidth that is the median bandwidth times 2 to the L, where L ranges from -20 to 0. So it's quite a wide collection of bandwidth of 21 bandwidth. And the tests we consider are our KSDAG test, the KSD median. This is just the KSD test where we use the median heuristic, the KSD split, where we split the data to select the bandwidth, and the KSD split extra data, which was written Oracle for MMDAG. This is the equivalent of Oracle, where we use extra data to select an optimal bandwidth. And here we observe that our KSDAG test matches the power of the KSD test that uses some optimal bandwidth. And it performs better than the split and that the median considerably better. So yeah, as I said, I haven't said it, but on the x-axis, we have the standard deviation of the noise. So when this is 0, this means that P is equal to Q. So all the tests have correct levels, 0.05. And then as we increase sigma, it's easier to distinguish P from Q, and all the powers increase. And our last experiment is MNIST normalizing flow, where we use the same collection of bandwidth. And so we have some normalizing flow. So a normalizing flow is just a generative model, but it has the property that it has some density, unlike GAN. So it's a generative model. We use a pre-trained normalizing flow. And so we have access to this density P. And the samples, so this is for our model P, and the samples will just use true MNIST samples. And this is, as I said before, in resolution 28 times 28. This is a high dimensional problem in dimension 784. So as I said before, like even though this looks like a really high number, the problem is inherently lower dimensional. So just as an illustration, the top row, those are digits from the true MNIST digit. The middle row was the digits sampled from the normalizing flow. So we can see that some digits really look like MNIST samples. They wouldn't be distinguishable by a human, at least not by me. However, some digits really do not look like digits. Some images drawn from the normalizing flow do not look like digits. And essentially, this is going to be because it has to interpolate from one digit to another. So sometimes it doesn't really look like a digit. And so what we do is we work in sample size 100 to 500, and we test the model normalizing flow, and we give it true samples MNIST. And so it has to see if it's able to understand that the true MNIST samples are not drawn from the model. And here we see that our KSDAG test really outperforms by a lot all the other tests. And essentially only our KSDAG test in this experiment is able to detect that the samples are not drawn from the normalizing flow. And we observe that we outperform the Oracle test, the one that the one that uses extra data to select an optimal bandwidth. And this is similar to before. The reason is probably that the way it selects this bandwidth is by maximizing a proxy for asymptotic power. And here we're in dimension 784. So, and we use only up to 500 samples. So we're definitely not in the asymptotic regime. So that's why this criterion does not work that well. However, we still observe that it works significantly better than the split and the median test. So just to conclude, similarly to the MMDAG, we aggregate KSD tests with different kernel bandwidths. We can do this with different kernels. We do not require data splitting. We obtain an upper bound on the uniform separation rate. And our results hold for quantile estimation using either wide or parametric bootstrap. And the results still hold for a wide range of kernels, and our KSDAG outperforms other adaptive state-of-the-art KSD tests. And just one more slide, what about the H-SIC AG? So for the independence problem, in the independence problem, we're given pairs of samples. So a pair X1, Y1, all the way to a pair Xn, Yn in RD1 times RD2. And we have access to, and they come from some joint probability density R. And they have marginal densities P equal to Q. And we have, is the product of a marginal equal to a joint probability or not? So this is essentially saying we have some paired samples, is the first component independent from the second component. And we can do this using the Hilbert-Schmidt independence criterion, the H-SIC. This is simply defined as the Mmd between the product of marginals and the joint probability density. And this would be using a kernel which just multiplies the kernels on X and the kernel on Y. And this has been done by Mélisande Albert and Béatrice Laurent, who are co-authors on the MMDAG paper, and Amandine Marel and Anwar Meinawi. So if you're interested, you can have a look. Just in terms of references, so we're done. Those are references for the aggregated test if you're interested, and those are the references for the tests we used for comparison in our experiment. All right, thank you very much for your attention. If you have any questions, I'll be happy to answer them.
Yeah, thank you very much for your very nice talk. It's very interesting. Okay, then let's thank the speaker again. Okay, so this is the end of the seminar.